Welcome to our deep dive into the world of operating systems.
Okay.
Today we're looking at a 2024 research paper
Okay.
titled Rusty Linux, Advances in Rust for Linux Kernel Development,
Right.
which you sent our way.
Yes.
So you're clearly interested in how Rust is going to change kernel development.
Absolutely.
And that's exactly what we're going to be talking about.
Great.
Rust is being hailed as the solution to a problem that's been around for decades, memory safety vulnerabilities.
Yeah, that's a big one.
So let's step back for a second.
Sure.
Why is memory safety such a critical concern when it comes to operating systems?
Well, operating systems are the bedrock of our digital world.
Okay.
Everything you do on your computer relies on the operating system's kernel
Right.
to manage resources and execute programs safely.
It's the foundation on which everything else is built.
Exactly.
So any vulnerability in that foundation can have cascading effects.
Yes, impacting the security and stability of the entire system.
And memory safety vulnerabilities are a hacker's dream.
Oh, absolutely. They can allow attackers to take control of your computer,
Okay.
steal your data, or even crash the entire system.
It's like those hacker movies from the 90s.
Yes, those predictions weren't too far off.
And the scary part is that these vulnerabilities are often the result of simple programming errors
Right, and they can be incredibly difficult to detect.
and prevent.
Yes.
So for decades, the go-to language for building operating systems has been C,
Yeah.
powerful, efficient.
Right.
But as we've said, it has a memory safety problem.
C's lack of built-in memory safety mechanisms has been a well-documented Achilles heel.
It offers great flexibility and control over memory management
Yes, but it also places a heavy burden on developers.
to ensure memory safety manually.
Precisely.
It's like walking a tightrope without a safety net.
And those missteps happen more often than you might think.
Even experienced C programmers can make mistakes that lead to vulnerabilities.
Like buffer overflows,
Yeah.
dangling pointers, and use after free error.
So it's not just hypothetical risks,
No, these vulnerabilities have been exploited in countless real-world attacks
causing billions of dollars in damage.
and compromising sensitive data.
This problem has even reached the highest levels of government.
That's right.
The White House report calling for a shift away from memory-unsafe languages.
Yes, just this year.
Okay.
The White House Office of the National Cyber Director issued a report
Okay.
emphasizing the need to move away from memory-unsafe programming languages.
In critical software infrastructure.
They recognize this as a national security issue.
So where does Rust fit into all of this? Is it the silver bullet that everyone's been hoping for?
Rust has emerged as a promising solution,
Okay.
but it's not just a simple replacement for C.
Ah.
It's a fundamentally different way of thinking about programming.
The paper specifically focuses on Rust's integration into the Linux kernel.
Right, but researchers are already exploring the use of Rust across a wide range of kernel architectures.
Like
Microkernels,
Okay.
unikernels, and even exokernels.
So what makes Rust so special?
Rust's core innovation lies in its ownership model and compile time checks.
Okay, let's unpack that a bit.
Sure.
What exactly is the ownership model,
Yeah.
and how does it contribute to memory safety?
In essence, the ownership model dictates that every piece of data in memory has a clearly defined owner at any given time.
Okay.
There are strict rules governing how ownership can be transferred or shared.
And the compiler enforces
Yeah.
these rules.
Meticulously, yes.
So it's like a very strict librarian
I like that analogy.
who keeps track of every book and makes sure it's always in the right hands.
That's a good way to think about it.
This system eliminates the possibility of dangling pointers or use after free errors.
Because the compiler is constantly tracking who owns what
Okay.
and ensuring that no one is accessing memory they shouldn't be.
And these checks happen at compile time.
Absolutely.
That's crucial.
If the code violates these ownership rules, the compiler will refuse to build the program.
Okay.
This prevents those memory safety vulnerabilities from ever making it into the running system.
So Rust's ownership model acts like a safety net at the very core of the software development process.
Precisely.
And this is a major departure from traditional languages like C.
Where the responsibility for memory management rests entirely on the developer.
This all sounds very promising,
Yeah.
but there's always a but, right?
Of course, no technology is perfect.
So what are some of the challenges that Rust faces in the world of kernel development?
Well, C has enjoyed a significant head start in terms of optimization, speed, and efficiency.
It's been the dominant language for operating systems for over 4 decades.
That's right. And there's a vast amount of knowledge and experience built around it.
So can Rust really keep up with the performance demands of an operating system kernel?
That's one of the key questions that researchers are exploring.
Rust is a relatively young language,
And there's ongoing work to ensure that it can match C's performance
especially in critical areas like memory management.
and real-time capabilities.
The research paper mentions some specific studies that looked at Rust's performance.
Yes, and the results are encouraging.
For example,
One study investigated implementing a UDP driver in Rust within the Linux kernel,
using.
the Rust for Linux project.
Okay.
While still in its early stages, the performance was only marginally slower than the equivalent C implementation.
So there's hope that we won't have to compromise on performance for the sake of security.
That's the goal, but performance isn't the only challenge.
What else?
Another significant hurdle is the sheer size of existing code bases
Operating systems like Linux have millions of lines of C code.
that have been meticulously crafted and optimized over decades
Integrating Rust into that environment requires careful consideration.
of interoperability and potential performance impacts.
It's like trying to renovate an ancient cathedral while still holding Sunday services.
A very apt analogy.
And there are other considerations as well.
Yes, such as, for one, Rust has some missing features that kernel developers rely on.
Right.
Better isolation mechanisms.
What about the issue of panics?
Yes, panics in Rust are essentially unrecoverable errors.
That can.
Cause the program to terminate abruptly,
In a user space application, a panic might just crash the program.
which is an inconvenience.
However, in an operating system kernel,
A panic can bring down the entire system.
so it's like a single point of failure.
Exactly.
And that's why managing panics is a critical concern in kernel development,
The research explores various strategies for handling panics,
such as.
containment within specific modules or mechanisms for graceful recovery.
So it's about damage control, trying to prevent a single panic from causing a system-wide meltdown.
Precisely.
But it's a complex problem.
And finding the right solutions is an active area of research.
This brings us to a fascinating philosophical question raised by the Theseus OS research mentioned in the paper.
Ah, yes, the question of soundness versus safety.
Can you elaborate on that for our
Not
listeners?
sure.
What's the distinction between those two concepts?
Soundness refers to the ability to prove mathematically that a system is free from all possible errors.
So it's like a theoretical guarantee of perfection.
In a way, yes.
Okay.
Safety, on the other hand, is a more pragmatic concept. It's about minimizing the risks of errors.
And ensuring that the system can handle unexpected situations gracefully.
Exactly.
So safety is about building resilience.
Even in the face of imperfections.
And the research suggests that even with a memory-safe language like Rust,
It's likely impossible to create a completely sound operating system,
there will always be areas where we have to rely on unsafe code.
such as when interacting directly with hardware
Okay?
or when performance requirements demand low-level optimizations.
So it's about striking a balance.
Between the ideal of soundness and the practical realities of building complex systems.
And of course, community support plays a vital role in the success of any new technology.
Absolutely.
How is the developer community responding to this potential shift towards Rust in kernel development?
There's definitely a growing interest in Rust within the kernel development community.
Yeah.
There's also recognition that there's a learning curve.
It's a new way of thinking about programming.
Precisely.
Rust's focus on ownership and borrowing can be challenging for developers who are used to traditional languages like C.
Yes, but there's a willingness to learn and adapt.
It seems we've only just scratched the surface of this fascinating world of Rusty operating systems.
We have a lot more to discuss.
But before we dive into the specifics of the challenges and opportunities presented by Rust,
Okay,
I'd like to pause here and give you a moment to reflect.
sure.
What are your initial thoughts on this potential shift towards Rust in kernel development?
It's certainly a pivotal moment in the evolution of operating systems.
What do you see as the potential impact of this shift?
I believe the potential impact is enormous.
Okay.
Rust offers a compelling combination of safety performance and expressiveness.
If it proves successful in the realm of operating systems,
It could have a ripple effect throughout the entire software industry,
leading to?
a new era of more secure and reliable software systems.
But as we've discussed, there are challenges to overcome.
And the journey is just beginning. The potential for Rust to enhance software security is vast, and that extends beyond just operating systems.
That's an interesting point. We've been focusing on operating systems,
Right?
but could Rust's influence spread even further?
Absolutely. If Rust proves successful in the demanding realm of kernel development,
Right.
it could pave the way for wider adoption.
Yeah.
other critical software infrastructure like network devices, industrial control systems, and even financial systems.
So the implications extend far beyond just making our computers run more smoothly.
Yes.
We're talking about potentially safeguarding the systems that power our entire digital world.
Precisely. But let's dive back into some of the specific challenges that Rust faces within operating system development.
We touched on the massive size of existing C code bases
Yes.
and the delicate dance of integrating Rust into these environments.
Right.
Could you elaborate on the challenges of bridging these two worlds?
It's not as simple as just swapping out C code for Rust.
Operating systems like Linux have evolved over decades.
With millions of lines of C code that have been meticulously crafted and optimized.
The transition to Rust requires a nuanced approach.
Carefully considering how to integrate new Rust code with these existing C components.
Without
Introducing performance bottlenecks or compromising stability.
The research paper highlights some specific examples of these integration challenges.
One study focused on developing a file system module, the Linux kernel, written entirely in Rust.
Okay.
While the project was ultimately successful, the authors emphasized the difficulties of interfacing with the kernel's existing C APIs,
These APIs were not designed with Rust safety guarantees in mind.
requiring careful adaptation and potentially impacting performance.
It's like trying to fit a square peg into a round hole.
In a sense, yes.
And it's not just about making the code work together.
No.
It's about ensuring that the performance doesn't suffer.
The way Rust manages memory and handles errors can be quite different from how C does it.
And these differences can introduce overhead if not carefully managed.
That's right.
This raises the question of performance optimization.
Okay.
How are researchers tackling the challenge of making Rust code run as efficiently as possible in kernel environments?
Especially when compared to the long-standing dominance of C.
Right.
There are several promising approaches being explored.
Right.
One strategy focuses on improving the Rust compiler itself,
Optimizing.
its code generation to produce more efficient machine code.
So it's about leveraging the power of automation to enhance performance.
Exactly. And another approach involves developing specialized libraries and frameworks,
For
kernel development, that are specifically optimized for performance,
these libraries can provide low-level primitives and abstractions,
that are tailored to the unique demands of kernel code.
allowing developers to write high-performance Rust code without having to reinvent the wheel.
Yes.
The Rust for Linux project, which we mentioned earlier, seems to be a prime example of this.
The Rust for Linux project is a key initiative in this area.
It aims to provide a safe and efficient way to write Linux kernel modules in Rust.
And it's already being used to develop real-world kernel components with promising performance results.
So the ecosystem surrounding Rust for kernel development is maturing rapidly.
It's certainly gaining momentum, which is encouraging.
As the ecosystem grows, we can expect to see even more innovation and progress in this area.
I agree.
Now let's switch gears for a moment and delve into the fascinating world of panics in Rust.
Okay.
Can you elaborate on what panics are?
And why they pose a unique challenge in kernel development.
As we touched upon earlier, panics are Rust's way of signaling unrecoverable errors.
They represent situations where the program cannot safely continue execution.
So it's like hitting a brick wall.
A very apt analogy,
In a typical application, a panic might simply crash the program.
which is inconvenient but not catastrophic.
However, in an operating system, kernel,
Right.
which controls all the essential functions of a computer.
A panic can bring down the entire system.
So the stakes are much higher in a kernel environment.
Absolutely. And that's why managing panics is crucial in kernel development.
The research we're examining explores various strategies for handling panics effectively.
Such as containing them within specific modules,
Sure.
providing mechanisms for graceful recovery.
So it's about building in safeguards to prevent a single panic from cascading into a system-wide meltdown
Precisely, it's about creating a more resilient system.
that can gracefully handle unexpected errors without compromising stability.
Exactly.
The research highlights some specific approaches to mitigating the risks associated with panics
Okay.
in a kernel context.
One intriguing approach involves the use of panic handlers.
What are those?
These are specialized functions that can intercept panics, attempt to recover from the error, or at the very least provide more informative error messages.
So it's like having an emergency response team on standby, ready to step in when a panic occurs.
A good way to put it, and interestingly, Rust's emphasis on memory safety can actually help mitigate the risk of panics to some extent.
Because
Rust enforces memory safety at compile time.
so many of the errors that would lead to panics in a C program are simply not possible in Rust.
That's right.
So Rust safety features can help prevent some panics from happening in the first place.
Exactly.
But we still need those safeguards in place.
They're the truly exceptional circumstances, yes.
And this is an area where ongoing research is crucial.
Finding robust and efficient ways to handle panics in a kernel environment
Is essential for the wider adoption of Rust in this critical domain.
I agree.
We've spoken extensively about the technical challenges.
Right.
But what about the human element?
Okay.
How is the developer community responding to this potential shift towards Rust in kernel development?
It's an exciting time for developers who are interested in operating system development.
As with any new technology, there's a learning curve.
But the Rust community is known for being incredibly welcoming and supportive.
So it's a good environment for learning and experimentation.
Absolutely. And the potential rewards are significant.
What advice would you give to developers who are intrigued by the prospect of working with Rust in operating systems?
I would encourage them to dive in and start exploring.
The best way to learn is by doing,
There are tons of resources available online,
including.
documentation tutorials, and open source projects to contribute to.
So there's no shortage of opportunities to get involved.
Not at all. And by participating in the Rust community,
Developers can not only learn valuable skills.
but also contribute to the advancement of this important technology.
We've primarily focused on the Linux kernel,
Right.
but the world of Rust-based operating systems extends far beyond that.
There's a whole ecosystem of them out there
Can you tell us about some other notable projects?
that are pushing the boundaries of what's possible with Rust,
Absolutely. One project that stands out is Redux.
which aims to be a full-fledged Unix-like operating system written entirely in Rust.
So it's a clean slate approach, leveraging the unique features of Rust to build a new kind of operating system.
Precisely, and it's not just about replicating existing operating systems in Rust.
It's about exploring new ideas and architectures that were simply not feasible with traditional languages.
That's right.
Another project that caught my attention is Theseus,
Okay.
which takes a very different approach to operating system design.
Theseus is fascinating because it leverages Rust's features
To achieve
a level of isolation and modularity that was previously unheard of in operating system design,
It's built around the concept of cells.
which are self-contained units of code that communicate with each other through well-defined interfaces.
So it's like breaking down a monolithic kernel into smaller, more manageable components.
A perfect analogy, and because Rust enforces memory safety at compile time
These cells can be isolated from each other.
in a way that prevents one cell's errors from cascading and affecting the entire system.
That sounds incredibly robust. Are there any other Rust-based operating system projects that you find particularly interesting?
There's one called Talk.
What's that?
It's specifically designed for embedded systems.
Okay.
It leverages Rust's safety features to create a secure and reliable platform.
For running,
Applications on resource-constrained devices.
particularly in the Internet of Things.
Exactly.
So it's bringing the power of Rust to the world of tiny, interconnected devices.
Precisely.
The implications of that are quite significant considering the security concerns surrounding the Internet of Things.
Security is often an afterthought in the embedded world.
But as more and more devices become connected to the Internet, the stakes are getting higher.
Talk is an example of how Rust can be used to build a more secure foundation.
For this rapidly expanding interconnected world,
That's right.
it's a reminder that security is not just a concern for big servers and desktops.
It's something we need to consider at every level of the computing stack.
From the tiniest sensor to the most powerful supercomputer.
I couldn't agree more.
Now we've explored a wide range of applications for Rust in operating systems.
From massive kernels to tiny embedded systems.
But what about the broader software development landscape?
Okay.
Do you think Rust is destined to become a mainstream language? Or will it remain primarily in the realm of systems programming?
That's a question that's generating a lot of discussion.
Rust certainly has some compelling advantages.
That could make it appealing for a wider range of applications.
Such as?
Its emphasis on memory safety,
Okay.
its expressive type system, and its performance characteristics.
Make it a strong contender for any application where reliability and security are paramount.
That's right.
So it's not just a niche language for systems programmers.
Not at all. We're seeing Rust being adopted in web development, game development, data science, and even in fields like machine learning and artificial intelligence.
So its versatility is becoming more apparent,
Exactly. And its popularity is growing rapidly.
thanks in part to its active and welcoming community.
And the wealth of learning resources and open source libraries available.
But there are also challenges to wider adoption rate.
Of course, one challenge is the learning curve.
Rust's ownership and borrowing system.
Can be difficult for newcomers to grasp,
It requires a different way of thinking about programming.
and it can take some time to master.
So it's not a language you can just pick up overnight.
Not necessarily, but I would argue that the payoff is worth the effort.
Once you understand the core concepts of Rust, you can write code that is incredibly safe, efficient, and expressive.
I agree.
Another hurdle to widespread adoption might be the perception that Rust is a complex and intimidating language.
That's a common misconception.
While Rust does have some advanced features,
The core language is actually quite elegant and straightforward,
and the compiler is very helpful.
providing clear error messages and guiding developers towards writing correct code.
So it's more approachable than its reputation might suggest.
Yes, and the community is very supportive with a wealth of resources available to help developers of all skill levels.
It sounds like Rust's future is quite bright.
I believe so.
But it's important to acknowledge that no technology is without its risks.
That's true.
What are some potential downsides or risks associated with Rust that we should be aware of?
That's a crucial question to consider. While Rust offers significant advantages in terms of memory safety.
It's important to remember that it's not a silver bullet.
Right.
What are some of the potential pitfalls we should be mindful of?
One potential risk is that the laser focus on memory safety could inadvertently come at the expense of other important considerations, such as performance or flexibility.
So it's a delicate balancing act,
Exactly. It's important to remember that memory safety is just one aspect of software quality.
albeit an essential one.
We need to be cautious about sacrificing other critical goals in the pursuit of absolute memory safety.
Are there other potential drawbacks we should consider?
Another concern is that the complexity of Rust's ownership and borrowing system, while powerful, could lead to more subtle and difficult to debug errors.
The compiler is excellent at catching memory safety errors.
But it's still possible for developers to introduce logical errors or unintended consequences,
That can be challenging to track down.
especially for those who are new to Rust.
So Rust can help us write safer code.
But it doesn't eliminate the need for careful design, thorough testing, and good old-fashioned debugging skills.
Precisely. Rust is a powerful tool,
Yeah.
but it's still just a tool. The responsibility for writing high-quality software ultimately rests with the developer.
I agree.
And that brings up another important point,
Okay.
the question of governance and ecosystem sustainability.
Who is responsible for maintaining and evolving the Rust language and its ecosystem?
Is there a risk of fragmentation or vendor lock-in as Rust gains wider adoption?
That's a valid concern. Currently, the Rust project is governed by a core team of developers. A large and active community which has been remarkably successful in fostering collaboration, making decisions in a transparent and inclusive way.
However, as Rust continues to grow,
It will be important to ensure that the governance structure remains sustainable.
and that there are clear processes for decision-making and conflict resolution.
Exactly, and that's a challenge that many open source projects face as they mature.
But based on the Rust community's track record, I'm optimistic that they will navigate these challenges effectively.
I am too.
It's encouraging to see how a community-driven project like Rust can evolve and adapt to the demands of wider adoption.
It's a testament to the power of open source collaboration and the shared commitment to building a better future for software development.
We've delved into the technical intricacies of Rust, its potential benefits, and the challenges it faces.
Right.
But before we wrap up this exploration,
Okay.
I want to shift gears for a moment and ask you a more philosophical question.
Sure.
We've talked about the potential of Rust to make software safer and more reliable.
Yes.
But beyond the technical aspects,
Okay.
what do you think are the broader implications of this shift towards memory safety?
What does it mean for the future of software development and the way we interact with technology?
That's a profound question, and one that I believe deserves careful consideration.
If Rust truly succeeds in transforming the way we think about and build software,
It could mark a fundamental shift in our relationship with technology.
for decades we've accepted software crashes, security vulnerabilities, and data breaches.
As an inevitable part of the digital landscape.
But what if we could change that?
What if we could build software systems that are inherently more robust, more resilient, and more trustworthy?
It's a tantalizing vision.
A world where we can interact with technology with greater confidence and peace of mind.
Exactly, and that's not just a utopian dream. It's a goal that's becoming increasingly attainable.
Thanks to innovations like Rust.
Right.
But achieving this vision requires more than just technological advancements, doesn't it?
It requires a fundamental shift in mindset.
A recognition that security and reliability are not just technical considerations.
but essential values that should be embedded in every stage of the software development process.
And that shift in thinking from reactive to proactive
Could have far-reaching consequences not just for the software industry, but for society as a whole.
as our dependence on software continues to grow. The quality and reliability of that software become increasingly critical.
From self-driving cars to medical devices to critical infrastructure, the systems that shape our lives are increasingly reliant on code.
And the consequences of software failures are becoming more severe.
So the stakes are higher than ever.
Absolutely. And that's why the emergence of languages like Rust is so significant.
It represents a new paradigm in software development.
One that prioritizes safety, reliability, and trustworthiness.
It's a hopeful sign that we're moving in the right direction.
But as you said earlier, this is a journey, not a destination.
That's right.
What are your thoughts on the next frontiers in this world of Rusty operating systems?
What are the most exciting areas of research and development that you're keeping an eye on? The landscape is evolving rapidly, and there are several fascinating avenues of exploration.
That whole immense promise.
Yes.
What are some of the key areas that you're particularly excited about?
One area that's particularly intriguing is the development of formal verification techniques for Rust code.
Formal verification involves using mathematical proofs
To rigorously demonstrate that a piece of code behaves exactly as intended.
eliminating the possibility of certain types of errors,
Yes, and this is especially important for operating system kernels.
where even the smallest error can have catastrophic consequences.
The research we've been discussing highlights some promising advances in this area.
With researchers developing tools and techniques for formally verifying Rust code at different levels of abstraction.
Right.
That sounds incredibly complex.
It is.
Are these tools something that everyday developers will be able to use, or is this more of a specialized field?
Formal verification is definitely a specialized field right now, but there's a growing movement to make these tools more accessible and user-friendly.
The goal is to eventually integrate formal verification into the standard Rust development workflow.
So that developers can benefit from these powerful techniques without needing to become experts in formal methods.
So it's about democratizing these tools and making them available to a wider audience.
Exactly.
That's an encouraging trend.
It reflects a broader shift in software engineering towards greater rigor and reliability.
Another area you mentioned earlier is the ongoing challenge of optimizing Rust code for performance in kernel environments.
As we discussed, there are several promising approaches being pursued.
One is to continue improving the Rust compiler itself.
Optimizing its code generation to produce more efficient machine code.
So it's about making the compiler smarter and more efficient.
Precisely, and the other approach involves developing specialized libraries and frameworks for kernel development that are explicitly designed for performance.
These libraries can provide low-level primitives and abstractions that are tailored to the unique needs of kernel code,
providing developers with the right tools and building blocks to write high-performance Rust code from the outset.
Exactly. We're seeing the emergence of such libraries like the Rust for Linux project we discussed earlier.
The Rust for Linux project is a prime example of this effort to create a robust ecosystem for high-performance Rust development within the Linux kernel.
It sounds like the convergence of these two approaches
Optimizing the compiler and developing specialized libraries
holds great potential for closing the performance gap between Rust and traditional languages like C.
I agree, and as research and development in this area continue to advance,
we can expect to see Rust becoming an increasingly viable option for performance-critical applications.
That's right.
We've covered a lot of ground today exploring the technical nuances of Rust, its potential benefits, and the challenges it faces in the world of operating system development.
It's been a fascinating discussion.
But before we conclude our deep dive,
Okay.
I want to circle back to the broader implications of this technological shift.
Sure.
Beyond the technical aspects, what do you think are the societal and ethical implications of this move towards memory safety in software?
That's a crucial question.
What are your reflections on the broader impact of this shift?
As we discuss, the software that underpins our lives is becoming increasingly complex and interconnected.
From healthcare systems to transportation networks to financial markets, our reliance on software is only growing.
And with that growing reliance comes heightened responsibility.
The consequences of software failures are no longer just technical glitches.
They can have real-world impacts on people's lives, livelihoods, and even safety.
Precisely, and that's why the push towards memory safety and software reliability is so important.
It's not just about preventing crashes and security breaches.
It's about building a more resilient and trustworthy digital infrastructure that can support a flourishing society.
I wholeheartedly agree.
The emergence of languages like Rust gives us hope that we can create a more secure and reliable digital future.
It's a sign that the software development community is rising to the challenge, recognizing the responsibility that comes with creating the systems that shape our world.
But it's not a responsibility that falls solely on the shoulders of developers, is it?
No, we as users of technology also have a role to play.
By understanding the importance of software security, by demanding better from the companies that create the software we rely on, and by supporting initiatives that promote digital responsibility.
We can collectively contribute to a more secure and reliable digital future.
That's an excellent point.
Yeah.
This is a shared responsibility. We all have a stake in building a better digital future.
And by working together, by combining technical innovation with ethical awareness, we can create a digital world that is not only powerful, but also safe, reliable, and worthy of our trust.
That's a vision worth striving for.
I agree.
I think that's a perfect place to pause our exploration. For now, we've delved deep into the world of rusty operating systems.
Right.
But it's clear that the implications of this technological shift extend far beyond the technical realm.
The conversation is just beginning.
Before we move on to the final part of our deep dive, I want to give you a moment to gather your thoughts.
Okay.
What are your key takeaways from our exploration so far?
What stands out to you as the most significant aspect of this shift towards memory safety in software development? The potential for transformation is immense.
What are your hopes and concerns as we venture into this new era of software development?
I believe we're on the cusp of a new era in software development.
On where?
Safety, reliability, and trustworthiness are no longer afterthoughts, but core values.
It's an exciting but challenging prospect. This vision of a more secure and reliable digital future.
It is.
As we've discussed, there are hurdles to overcome, both technical and philosophical.
Absolutely.
Before we conclude our deep dive,
Okay.
I'd like to shift our focus to you, our listener.
Right.
We've explored the complexities of Rust.
Its potential to revolutionize operating system development and its broader implications for software security.
What are your thoughts on all of this? What aspects of this conversation resonated most strongly with you?
It's always fascinating to hear different perspectives.
What insights or questions has this exploration sparked for you?
Perhaps you're wondering about the practical implications of this shift towards memory safety.
How might these advancements in operating system development affect your daily interactions with technology?
Imagine a world where your computer is less susceptible to crashes,
Caused by
memory errors,
where software updates are smoother and less disruptive because the underlying code is more robust.
These are just a few of the potential benefits that this shift towards memory safety could bring.
And it's not just about personal computers, is it?
No, we're talking about a transformation that could impact everything, smartphones and tablets to servers and cloud infrastructure.
The potential for positive change is vast.
But what about the challenges?
Perhaps you're concerned about the complexity of learning a new programming language.
Like Rust.
Or the potential costs associated with transitioning to a new technology.
These are valid concerns, and they underscore the importance of ongoing research, education, and community support.
To make this transition as smooth as possible, it's clear that this journey into the world of rusty operating systems is just beginning.
There's much work to be done both technically and culturally.
To fully realize the potential of this transformative technology.
And the conversation needs to extend beyond the realm of software developers.
We as users of technology have a role to play as well.
By understanding the importance of software security, by demanding better from the companies that create the software we rely on, and by supporting initiatives that promote digital responsibility.
We can collectively contribute to a more secure and reliable digital future.
I agree.
What are your thoughts on this shared responsibility? How do you envision your role in shaping the future of software development?
These are questions worth pondering as we continue to explore the evolving landscape of technology.
The decisions we make today will have a profound impact on the digital world we inhabit tomorrow.
Absolutely.
As we reach the end of our deep dive,
Okay.
I want to leave you with a final thought to consider.
We've focused on operating systems, the foundation of our digital world.
But the implications of Rust's memory safety guarantees extend far beyond that domain.
Imagine a world where all critical software infrastructure,
from network devices to financial systems to medical equipment,
is built upon a foundation of memory-safe code.
What would that world look like?
How would it change the way we interact with technology and trust the systems that underpin our lives?
These are questions worth contemplating as we venture deeper into this new era of software development.
Thank you for joining us on this journey of exploration.
We hope this deep dive has provided you with valuable insights.
And sparked your curiosity about the future of software development.
Until next time, keep learning, keep questioning, and keep diving deep into the fascinating world of technology.
I couldn't agree more.